crossing. I still have to speak in English. So, okay, last time we started talking about the connection. And let me real quick recall what was the definition. So I had the following starting data. So it's E is vector bundle over X. And then I have by definition connection, so connection on E is an R linear map well, from where to where? From sections on E to sections on E tensor cotangent bundle on X, satisfying the following properties here. If I take nabla of a section multiplied by a function, it is the same as applying nabla to a section plus, so I need to take df, well, s tensor df, since I wrote t star x in here. It's like that. So it's kind of Leibniz rule. So here, so for any f from C infinity of x and any s with a section right? And then we talked that two connections, they actually differ by the section of E star tensor E tensor T star X. Okay, so we need to go to coordinates. So this is like coordinate-free definition. So we would like to see what is going on in coordinates. For that, we need to see that actually it's well to restrict connection to some open subset of X. It's a well-defined operation. Namely, I want this claim so basically, if I have a F, some section of E, such that on some open subset, its restriction will just be then if I take nabla of F and then restrict it to, so it's a section of this, right? And then I restrict it to U, so I claim that this is actually zero. Okay. Well, this is a really easy statement. Just if I take this U, right, and I choose a point P inside U, any point, And then I would like to consider this function psi. This is function on C infinity of x. So this is one function, right, that looks like this. So I have u, and I have p inside. And so I have, this is my function, so it's outside of u, it's 0, and at some neighborhood around p it's 1, and then that's it. So this is my psi. I think we called this bump function. Then I know that psi f, right, this f, because of this condition, is just identically 0 on the whole manifold X, right? And well, of course, if I take, so it's R linear map, right? So if I take nabla of 0, it's 0. That is given, right? So therefore, I take nabla of this guy. Well, on one hand it's 0, on the other hand, well, I can use this Leibniz rule and write that it is psi nabla f plus f tensor d psi.
Excuse me, what's the symbol for the psi?
Just consider. It's an I. Consider. I don't know. Just I can. Sorry for. So consider.
How do you write this symbol? This is like angle.
No. This is just some I used. Yes, angle and then like this.
This means consider. Okay.
I don't think it means consider like worldwide, but in my notation system, it means that. Sometimes I write this, it means let. I don't know. Some people use it, some people, yeah. Пусть. Yeah, okay. So, anyways, right. So we can write it like this, just using Leibniz rule, and then I can, of course, take this and consider its value at p. Right. This will be then psi of p here, f of p, and here f of p, d psi of p. So this is 1, as we agreed, and this is 0, right? Because it's psi is constant around p, right? So the differential is 0. So therefore we have only this term left, and I have nabla. Well, nabla f. Here? Yeah. Sorry. It's like not Laplacian. Yes. It should be like that, right? Yes.
So psi is constant in some neighborhood of p.
Yes. Well, we can require that. Yeah, I never gave the details. It's just not really about differential geometry, but it's calculus. But you can construct such a function. Anyways, what we get is that this is equal to 0, and so that's exactly what we want. That's why you point p from u. Anyway, so that means that actually, if I have such nabla on vector bundle E over X, then this gives me a connection on a restriction of E to any open neighborhood of X. That was my message. So so let me write this down. So if I have nabla, which is connection on E, this gives me connection on, strictly speaking, another vector bundle connection. Which I actually denote by the same letter, on E restricted to U. Right, so I have sections now here, right? And I just defined. So let me take some section S from, it's a section of E restricted to U. So this doesn't know anything about what's going on outside of U. And then I need to define what is nabla of S. So far I can just apply nabla to the whole section, right? To section over the whole X, right? Strictly speaking. So I just define it by applying nabla to S tilde, where this is extension, any extension of S to the whole X. Okay? And because of the previous proposition, this is well defined, doesn't depend on extension. So if I have two different extensions, then I take difference of them. This will be my F, right? And then I apply this proposition and see the difference between nablas is the same. Okay.
Why does the extension exist?
Well, I guess you just can consider partition of unity. So you take U and everything outside of U. So the partition with two neighborhoods, right? And you have like a zero section outside and this inside, and you glue it by partition of unity. For example, such construction would work.
What about the boundary of, like, closer to the boundary of our open subset, where we take the unity here, the subset? The unity, we take it that it is one everywhere on the subset U.
Mm-hmm.
Yes. Right. And then somewhere else it like goes from 1 to 0. So there are like some points where it is non-zero yet. Or I'm mistaken. Or it's immediately 0.
No, it's not immediately zero.
Then what happens in those points? How do we define this extension or this section over there? Or we can just look at this statement as if the S wave was already given.
No, I really want any section to, like, in here. Well, you see, just by construction, kind of any section here coming from a restriction. So there's actually no such problem. So,
Why is that?
well, just from the definition of what is this vector bundle.
Okay.
Okay? So by definition, any section is coming from here. So no such problem. Yeah. All right. Yeah, but this is third question. Anyway, so let us continue. So now I can define what is called Christoffel symbols that I defined, like kind of already without these details in homework list. But so suppose that I have u, so let u inside x. Again, we have all the previous notations. E is like a bundle over x, and this is open. So suppose that this is first of all it's trivializing a neighborhood of E, and also coordinate neighborhood of x. So on x, so u gives me I can have coordinates, right, for x in u, and also coordinate neighborhood of x. Let me denote. So trivializing means that I can have basis of sections. So let me fix some basis. S1, blah blah blah, S, I don't know, R. So this is basis in well, gamma of E restricted to U. On the other hand, we also, so this is we fix this, and also we fix coordinates, x1, blah blah blah, xn. So these are coordinates. And then we can define the following. So I have number. I can take one of these sections and apply number to, so these are local sections, but because of the previous discussion, it's okay to apply number to one of them.
What does mean coordinate neighborhood of x?
It means, well, it means this, I have a chart. So this is a chart.
Okay.
And also it's trivializing for neighborhood for E. And so these are components of phi. Smooth chart. Smooth chart. Okay, and then, okay, so I apply and I get something inside where? Inside here, right? And this is at the top of U. This is also trivial, right? Because E is trivial and T star of x is trivial because we fix coordinates. We have basis dx i's, right? So therefore, I can just write the following. Sum over A from 1 to n, sum over beta from 1 to r, gamma, alpha, A, beta. So just decompose it in the basis, this guy. Tensor dxa. So these are some functions on U. They called Christoffel symbols. Okay, and so locally we have we now can use this functions to write how nabla acts on any section S locally. So if I take, so S is a section, I can restrict it to U and get section of gamma of E of U, and I can decompose it. So let me not write restriction because I will carry a lot of unnecessary notation then. So sum F alpha S alpha on U. So this is alpha from 1 to R. And then I just can combine this and Leibniz rule. And then I will get the following. I will get that. So let me write this a little bit. So I have nabla of S. So let me just, okay, this is some, one-line computation. So let me just write answer, and we will see that actually, well, it will be evident that answer should be like that. So sum over beta from 1 to R, sum over A from 1 to N, and then I have df beta over dxa plus gamma alpha A beta and here also F alpha. So gamma, here F alpha. Yeah, sorry, I need to also to sum over alpha, so let me try again. So sum over alpha here, F alpha, gamma, beta, alpha A.
Excuse me, may I ask about the indices in that sum?
Yeah, so let me finish this,
Okay.
and then we'll discuss. Yeah, so S beta tens dx. So I expand this in this basis, and these are coefficients. All right.
The S has the index alpha,
Yes.
and then the sum is over alpha or A.
No, A.
And the second index for summing is beta.
Yes. So you see, I take this, right?
Why it is said that this is on U?
Well, because this is basis only over U. It's not a global basis; it's a local basis. So I need to restrict S and then decompose it in this basis.
Okay, so this is the decomposition of the restriction.
Yes. Yeah. Well, I don't write restriction not to carry a lot of symbols, but so I take this, put it inside here, and then use this and Leibniz rule. So when I use, so this bit comes from, so in Leibniz rule I'm applying nabla to S alpha, and this bit coming from this term. Right, I'm applying nabla to S alpha, I will get this, and it goes through F alphas. So this is one term of Leibniz rule. And this is another term where I have df, right? And my df is expressed in terms of this basis dxa is like that. So it should be like that. All indices you can check, but I'm pretty sure they're all right here. So so we can think that, so sometimes you will see in the literature that locally, so that connection is something like D plus some function f. Well, this is not a function, rather, but this is like a section of E star restricted to U, tensor E restricted to U, tensor T star U.
And there is enough connection.
What's that?
There is enough connection.
Well, this is, yeah, so this, we need to understand what does it mean. D is actually exterior derivative, but what does it mean to apply exterior derivative to a section? Well, you can apply exterior derivative to a function, right? So, but here you kind of, you need to think about exterior derivative as component-wise. So you need to fix a basis first, right? And consider like component-wise exterior derivative. That's what this term is responsible for. Okay? And plus this, which is this f.
And why this decomposition of delta is only local?
Why is that what?
Why is it only local decomposition?
Well, because I cannot guarantee you the existence of global basis. If there's a global basis, then okay, no problem, we can do it globally. So, but this is only for you have global basis only for trivial vector bundles, which is not very interesting case, actually. All right. So, we went from not local to local. We see that we have such a formula very well. So, but the question is how we can go back from local to global. So, another way. So, if I have like some functions gamma, alpha, a, beta, right? I can actually define locally a connection like this, right? Over all trivializing coordinate neighborhoods, I can define connection. So the question is how these gammas should transform so that they will glue together to a global connection. Okay, so that's my next question. So the question, how gammas should transform on intersections of trivializing coordinate neighborhoods. In order to make to give me global connection. Well, for that, I have vector bundle, right? And it comes with clutching data, right? As we discussed. So, well, so suppose I have two U's now, U and U tilde, right? And on U I have S alpha and XA. So, and then I have all the same with tildes. S alpha tildes give me basis local at U tilde, and then XA tilde are coordinates in U tilde, right? And then I have clutching data. So this, which, well, usually we denote it as U tilde, right? But since there's only two, there are no other elements of a cover, so let me just keep it G. So this is function from U tilde intersection, sorry. To G L R. Right. So it's clutching function. Which is, well, which we have once we actually fix two bases, right? And we know how, so this G is actually the guy who gives me transformation between two bases on the intersection. That's how we define the clutching data. So actually I take G, right, and take SI. This is just by definition is S I tilde. And here for I from 1 to 1. So this is a vector, right? This is a linear transformation. And this is, well, at every, so this is actually, this is a function, an intersection, this is function, intersection, and this is function, intersection. So this is at every point in the intersection. And every I from 1 to 1. Okay, now, well, actually, I can expand this a little bit more. So I have that S alpha tilde is actually some so actually this G has like since I have bases, right, I can consider matrix corresponding to G, and so this will be G beta alpha S beta. So this is just the same as this, just more explicit. Okay. Now I will give you answer and we'll discuss why this answer is correct. So I'm thinking, so first of all, I need to think of gamma. So it has three indices, right? Alpha, beta, and A. Right? And so, well, if I consider its value at a point P, right? These are functions, so I can consider now its value at some point P. So it has three indices, and if we will now consider this as a big matrix, if you wish, right? So here alpha and beta run from 1 to R, and A from 1 to N. So this, we would like to consider this as an element of E. So fiber at P of E star, tensor fiber of E at P, tensor T P star X. So we have three indices, so we need to make sure which index corresponds to each factor here. So of course A corresponds to this factor, and then I need to be accurate about alpha and beta, so it's like that. Beta goes here, and alpha goes here. So why is that? We need to go back to this. Yeah, sorry. Maybe let me switch. So if I have beta alpha here, then I need to put alpha in here and beta in here. So this guy is something that is a section, and this corresponds to this alpha, this index alpha here. So which is this one, right? So this alpha is what eats a section, so therefore it's in the star. Now this guy is a value, so corresponds to this index in E. And this guy is a value in this tensor component, so corresponds to index A, which is in here. So now I think of this guy, and I kind of denote it as just gamma without indices. I want to avoid indices. So now I have three indices, and I know, I kind of order them, I know where they sit here.
Oh, why? But beside E star.
Well, I can think of it as a linear functional that eats.
Это что такое вот суть совершенно непонятно. Альфа это число натуральное.
Ну да.
Почему оно находится в касательном слое?
Оно не находится в касательном. Это вообще векторное пространство.
Да.
Вот. Но я про него думаю, на самом деле оно должно преобразовываться ковариантно.
Это как они преобразуются?
Вот, да, ну да. Поэтому я поставлю здесь звездочку. Это как бы вылезет сейчас.
Что значит преобразуется ковариантно?
Ну, это значит, что если я меняю базис S какой-то функции, то соответствующая, значит, компонента, соответствующая альфа, меняется как двойственный базис.
Понятно. Спасибо.
Вот. А это меняется как обычный базис бета. Ну, потому что вот я здесь вот изменил этот базис, вот я на это и домножу. А это как бы, изменится как двойственный, потому что она ест как бы с альфа. Ну, если это как бы не помогает, это слово ест, то как бы не обращайся на него внимания. Ну, вот то, что я сказал, что оно ковариантно, значит, преобразуется. Okay, so now the answer to this question, I will just write this answer, and again we'll see that this should be like that. So first, so this is not the section of E star tensor E tensor T star X as we figured, right? But there is a term corresponding like to this being a section, like this F over there. So anyways, we have gamma and gamma tilde. So we have gamma and gamma tilde corresponding to tilde, U tilde. So I need to apply G inverse transpose tensor G tensor dx over dx tilde transposed to gamma tilde. So that would be a transformation if gamma was a section of this guy.
Gamma, this is the set of this function.
No, I'm saying that point-wise, it's in a fiber, right? But this is actually not a section because it transforms not like a section. So if it was just like that, it would be a section. But I need additional term here, which is this one. Sum over A from 1 to n dg inverse over dxa.
Это все-таки не тензор, эта штука. Гамма это не тензор.
Гамма не тензор, да.
А что гамма принадлежит этой штуке? Что это значит?
Это значит, что в каждом, то есть потому это не, локально как бы она сидит вот в этих пространствах. А не тензор в том смысле, что он глобально не переклеивается так, как нужно. Вот, значит, на G. Вот, ну, опять же, это все разговоры такие, но вот конкретные формулы, вот они я вам как бы даю. Значит, на G, окей, G, and then tensor dxa. Sum over A, yes. So let's see. So this is just, taking this G, like this matrix, and then this is applied to the first index, to alpha here, right? That's what it means. Then this is applied to index which I put in here to beta, and this one is Jacobian just of the transformation from one coordinate to another is applied to index A. That's what it means. I just don't want to write a lot of sums, right? So I just write it in a tensor notation. Then, but this happens for every point. And then plus this guy. So this should be inside, also should be inside here. So I should think of this term as in here, right? How do I look at it? So this is like R by R matrix multiplied by another R by R matrix, right? So I think of this term as living inside E P star tensor E, right? So this guy is the same as endomorphisms of EP, right? So this lives in, well, of course I need to write point P everywhere here, right? Well, this is of P, this is of P, of P, of P, of P, everywhere. So then this is endomorphism of EP, and then the morphisms of EP is the same as this vector space. Okay, and so therefore I think I identify this with an element in here, and it's still in here. So all makes sense. All right, so this is the answer. Now, well, how to get it? It's well, one way to look at it is just a Macy computation, but let's see some. Well, at least let's see what should be done. So we have S, some section, right? And it can be decomposed in two ways. So it can be decomposed on the intersection. So, I don't know, proof, if you wish, but this is not a proof, but rather just looking into formulas, what's going on. You can decompose it like that, on intersection, or decompose it in terms of tilde, as tildes. But the other decomposition would be F alpha G inverse S alpha tildes. Because that's how connect S alpha and S alpha tildes are connected, right? And now I put, so now I need to see that nabla of this sum F alpha S alpha, right? And this is written in terms of gammas, right, without tildes, and in terms of S. It's the same as nabla tilde. Nabla tilde, I mean nabla in terms of S alpha tildes and gamma tilde, right? And then here I should put F alpha G inverse S alpha, this. Now I just, use again this formula. I think it's on this blackboard, this one. On each side, but on one side I will have gamma tildes here, on the other side gamma without tildes. So this is like an exercise in computing. And what we see at least where this term comes from. So I apply nabla tilde, right? And there is this term when I take a derivative of this guy. Here. So, but instead of f beta, I will have f beta g inverse, right? And then again, I use Leibniz rule. I will have derivative of g inverse with respect to x, to xa. Okay, and then g is because I need to go back from s alpha tilde to s alpha to compare two sides. So that's where this term comes from. And this term is just when you ignore coefficients and apply nabla to sections, right? So this term, because of the Leibniz rule, when nabla is applied to coefficients, and this one is when it's applied to sections, and that's what I mean. If I can pull out coefficients, it means that actually nabla gives me like a section over this guy, right? And this would correspond to this transformation.
Can you please repeat the explanation for how we apply nabla to G?
Nabla to
How we handle G in this case?
this one.
Yes.
Yeah, so this is a function. Well, you can, this is a function which is linear transformation. So it's like a matrix where each element is a function of this matrix. But so it's like a compact form of, of a sum linear, of some sum, right? And so then I use Leibniz rule and treat this as a function. This is a function. So this, I have to apply nabla to this, meaning that I need to take differential of this. Plus apply nabla tilde to this one, right? So when I compute differential of this, it will be differential of this plus differential of this. Differential of this will be the same as, will be cancelled with what I have on the left. And here I will have additional term, which is differential of G inverse. That's exactly it. And then this additional G is because I need to go back from S tildes to S to compare both sides. So I need to compare it in the same basis, right? So this is all like it's like a termed coefficient to coefficient comparison in the same basis. Yeah. Well, that's what's going on. Of course, I could, be very boring and just do it, this computation. But I think it's better to explain it like that. Anyways, so gamma is not really a section, so it has like a term corresponding for it to be being like a section, and another term which corresponds to like this term D in local.
Sorry.
Yeah.
Will we be taking derivatives over xa tilde, not xa? When we take nabla tilde of f.
We will, but then I need to go back from dx tildes
Yeah.
to dx.
Yes.
And then I will
We just
apply again Jacobian, which will give me a differentiation which is
Oh, so
I can put
cancels out.
yeah, so I can put tildes both in here or erase them
Yes.
simultaneously. So yeah. Okay. All right, so that's what's going on here. Well, we will use. So anyway, so if you have a connection and it's Christoffel symbols, you can build up new connections. For example, like dual connection. You just say, okay, let me in dual connection consider like a gamma with with switch indices, and it also satisfies this globally. So therefore, it defines for me like a global connection. So that's a way how you define new connections out of old ones. All right. So now, next thing I want to talk about is yes. So now we have like a connection is like a differentiation of a section, right, in some direction. In this form, it's just unspecified direction. But I also want to take this. So this means that I can, go to, so I can pick some vector in the fiber, right, and see how it changes if I slightly change point in the base. Basically, that's what's going on. We want to see from this local picture to global picture. So we want to see how it changes if I go far away along some curve on the base. So that's called a parallel transport, and that's our next discussion. So, anyways, again, we have a vector bundle over X, and suppose I have two curves. So let gamma from 0 to some positive number epsilon to X, and also gamma tilde, so this curve on X, and this is curve on E. So these are smooth curves. Yeah, by curve I mean that this is injective immersion. So gamma and gamma tilde is injective immersions, and so therefore this data gives me a curve on X or E. So smooth curves such that gamma tilde is a lift of gamma. So I have pi composed with gamma tilde is gamma. So actually now I need this lemma that says that I can extend gamma tilde to a section on E, right? So there exists section on E such that S of gamma of T is gamma tilde of T. Right, so what's going on is that, okay, we have E, we have base, right? And so in the base I have some curve, and then, well, this is like a 3D picture, right? And so this gives me at the top some curve gamma tilde, and so I can extend this to a whole section such that it goes through gamma tilde. So this is my S. This is E. This is and this is gamma. I don't know if this picture is helpful, then okay. If not, then forget about it. Okay, so let me prove it real quick. So proof goes like this. So if I have some T0, so let me first go locally. Right, then let me fix some chart, U phi. So it's a chart of X around gamma of T0. Right, so it's side X. And then, so T0 is somewhere inside here. Then
It's gamma here.
was that
Well, on the picture it's gamma zero.
gamma T0? Yeah. Yes. That's true. Gamma T0. Yes. And so what I want to mention, to observe, is that there exists I such that d phi I composed with gamma at T0 is not well, I need to maybe write it like that. T0 is not 0. Because this is immersion, right? So actually, there's some component that differential is not 0, right? Immersion means that the differential has no kernel, right? So it means that at least in some component, phi I are components of phi. Okay. So it means that there exists some component which is not 0 because d phi I of gamma is not 0. Okay, so therefore I can invert it locally by the inverse function theorem, right? So there exists eta, which is phi I gamma inverse. So this is for t close enough to T0. And then I define around T0, I defined S0 of X. So my goal is to define a section S, right? So first I will go locally define it around T0 as follows. It's just gamma of tilde of eta of phi I of X.
Why is it gated? It is enough to take only one component of the phi.
But why not?
It looks like,
We can take any which is not 0.
but we want to be able to reconstruct the gamma from below, right?
Yeah, well, S has a lot of freedom in how it continues.
Okay.
So that's okay to choose whatever you like, just so that condition is satisfied. 1, 2, 3, 1, 2, 3.
I, what is it?
Well, so phi is from X to Rn. And so I is just, yes, so phi of some X is just this. So these are components. This is just function from really from U to R for each fixed I.
I'm just worried that we just went up from X, and what will happen when we go down? Can we reconstruct all of the other components?
So we would like to reconstruct only at this. So we have again our S only restricted at this line. So that's the only thing that we will like to reconstruct, and we will be able because of how we construct D. So anyways, so we can check, right, that S, we just can check, right, that S0 of gamma of t is gamma tilde of t. Right? Well, you just put the gamma of t in here, and you see that gamma, you have phi I composed with gamma, and this is inverse to it. So you get t. Because let me just by definition of this, gamma tilde of eta of phi I of gamma of t. And this guy is the inverse of this by definition. So I get gamma tilde of t. So locally I get what I want.
Okay.
Around, like, if I go, so x of course cannot lie on the curve, but still inside U. But I don't care. It's still a smooth function which satisfies this. So Erica started, yes. All right. But now I would like to, consider like a cover just of this, and don't know if I want all these details or not. Maybe not. Let me just say that. Well, I just consider. So this is compact thing, right? I consider finite. So I think it's just each point, right? So I do this construction for each point t0 in here, right? From that I can consider finite subcover. So I have finite constructions like this for finite numbers of t0s, covering the whole gamma here, and then I use partition of unity for this finite cover, and this will glue all these S zeros together, and this will give me a section, like local section around gamma. But then I just extend it to the whole by zeros outside. So that's just clear how to go from local to global from there. But the trick is to construct the inverse of such one. So then take cover of gamma of t by such a U, right? And using partition of unity, construct this. Okay. Anyways, so once I have this, just for to name this guy somehow, S. So by definition, S is called an extension of gamma tilde of t. And then I have this definition, another definition. Gamma tilde is called parallel with respect to gamma. I keep the same notation as in the previous lemma. If nabla v s of gamma of t equals 0 for any t from 0 to epsilon, so where my curve is defined, and any extensions S and V of gamma tilde and gamma respectively. And gamma, so this one should not be gamma, so there also should be section gamma prime of t respectively. So this is a curve in where? So this is curve in Tx. Right? And so V is an extension of this curve, S is an extension of this curve. And so we have this. By the way, yeah, I never discussed what is nabla with lower index V. So it just means that, well, I take nabla E of S. So I take nabla of S, right? So this guy belongs to the gamma of E tensor T star X. Right, and then I have this component, right, and I evaluated this component, right, the second one, this one, on and then this becomes a section of. So when I keep it without V, it means that it's a differentiation of a section in unspecified direction. I just keep it T star X. When I would like to differentiate in some specified direction, I take T star X and evaluate it at V, at something from Tx. Right, and then this gives me derivative of S in the direction of V. This also is called the covariant derivative. So nabla V is called the covariant derivative. Okay, any questions about this construction?
Can you please again explain what this means to extend gamma prime t? So gamma prime t is a curve of Tx, and
Yes.
it takes a section of Tx.
Yes,
Okay.
which is vector field.
Okay.
Yeah. So the same construction. Before we had just any vectors, vector bundle, and you specify taking this vector bundle. So you apply this construction two times. One for just vector bundle E, another one for more specific vector bundle Tx. And so we have a curve in Tx. We have extension of this to a section which is vector field. And so inside, so this is so V is really a vector field, and so I can, at each point I can, evaluate covector field and vector field. So that's what's going on here. All right. So my finish at 10:20, right? Okay, so let me try to check the following thing. So I gave some definition, and I need to worry whether it depends on S and V. So it should depend only on gamma and gamma tilde, not on extensions, right? And so my statement is that the snubber V of S depends, again, in this setup, depends on gamma and gamma tilde only. So I need to go local here. So locally, V is sum over Vi d of dxi. And so it's a vector field, as I figured. And S also can be decomposed. Sum over F alpha, S alpha. So I fix S alphas, fix coordinates, and so I write locally V and S like that, right? Then I can write what is nabla V of S, right? So just an answer. So it's sum of beta from 1 to R, sum of A from 1 to N, df beta over dx AVA plus F, right, again, sum over alpha, F alpha gamma, beta alpha A, VA, S beta. So I claim this. So I just need to go back. I don't know where it was, maybe here. So I need to go back all the way to here and evaluate this at the vector field sum Vi dxi, d of dxi, right? So when I evaluate this form related on d over dxi will give me delta ai, right? And therefore sum over a is the same as sum over, will give me index for v, and this is basically it. So instead of this guy, I will have VAs. And so that's exactly what is going on there. So it's a relation of previous formula on this guy. Right. Now I just need to see that everything here can be expressed through gamma and gamma tildes. Well, at a point P. So now I need to take this and put it, see its value at point P. So, okay, what is P? P, so let me just take some point on the curve. This is my P. Then I need to consider this at P and then this at P. Okay. So take. Then I have VA of P. I will have in this expression. So this is what? This is actually, I can write gamma A prime of T, where gamma A are components of my curve gamma, right, in this map. So I have phi A composed with gamma of T. So this is my gamma A. this is just from the definition. So this is an extension of gamma prime of t. Remember? So this is an extension of gamma prime of t. And because of that, the A of p is just like that at the point t, at the point gamma of t. Right, what else do I have there? I also have, so if, so I have f alpha of p also here. F alpha of p is just gamma alpha tilde of t, right? So gamma tilde is a curve. I can decompose it in, well, anyways, it's just, well, yeah, so f alpha at p is just gamma alpha tilde of t. It's just coefficients of the components of this curve decomposed in S alpha, right? So this depends on gamma tilde only, this depends on gamma. What else? I also have d of beta or dxa. But I need the whole expression here. So I'm claiming that sum over a df beta over dxa dA. Well, this is the same as applying v to f beta to at point p. Right? Just by definition, what does it mean to apply vector field to a function? But then again, it is the same as d over dt f beta of gamma of t, actually, right? Because v is an extension of gamma prime of t, so that's how I apply gamma prime of t to a function f beta by definition, right? Gamma prime of t is a differentiation, right? So that's how I apply differentiation in the direction of the curve. So that's how I do that. But then this guy is just, since f alpha at p is gamma tilde alpha at t, this is just gamma tilde prime beta at t. Well, just because just by definition, gamma tilde is composition of beta and gamma, just by definition. So therefore, this guy is also does not depend on extension. It's just gamma beta prime tilde of t. Yeah, this index means it's just really derivative of this function. It's not a derivation along this curve. This is like a function. I take its derivative at a point t. Anyways, we proved the proposition, but and as beta, yes. So as beta at gamma t, right, is where it is written. Yes, S beta of gamma t is just S beta at the point. So we fix a basis. It doesn't depend on extension. It's just our fixed basis. Right. So S beta, they do not depend on S. Okay, but why did I go local again? Right, this formulas with indices, because well, we proved everything, right? So nothing depends on really on extensions, only depends on gamma and gamma tilde. But I also want to, write this formula that we will use in the future. This is just a This is just how covariant differentiation looks in coordinates. So it is sum over beta gamma beta tilde prime of t plus sum over alpha and a gamma tilde of t gamma a prime of t. And then I have big gamma, which is Christoffel symbol, beta alpha a. Yes, beta. So yeah, so we will use this coefficient. You see, so in the future, so I'll just box it, and so we have this result. We will use it in the future. So in particular for parallel support, parallel curve along some curve in the base is given by some differential equation, which is saying that this should be zero.
Do you mean particular gamma is
Yeah, with some index, yes. Yes, alpha. And also we will introduce geodesic in like next time. Maybe not, I don't know. We'll see. And this also will become, so this guy equal to zero will become equation for geodesic as well. So this is an important formula.
And so in this previous formula, sum over A applies to whole.
Sum over A applies to
So it's like
the
sum
whole
over
thing.
A.
Yes, yes. I think I should maybe, yeah.
Or
How
we should just add A to sum over A.
Yeah, maybe I need to do it like this. Also, I can factor out the A, but I really needed this whole expression here because this whole expression really depends on gamma tilde. Okay, so let me stop here. Let's have a break for 5 minutes, then proceed.